Hey BC, it is Mr. Canfield. Today we're doing calculus and parametric equations. So there's a couple big ideas and we'll start with the first one. So, we have, let's say x is equal to 2t minus 5 and y is equal to t squared minus 8t plus 2. Let's say we have that. So we could take the derivative of each of these separately. We could get dx dt and get 2. We could get dy dt and get 2t minus 8. But how could I get dy dx? So, and let's talk about the benefit of something like this. So if we have a parametric, remember that the way that this works is we're essentially x and y are two independent coordinates that are moving around based on time. And it's going to be some kind of weird squiggle sometimes. And we want to be able to say any point, if I plug in that point, that x comma y point, what's the slope at that point? These are only the change in the x coordinate and the change in the y coordinate. The cool thing is, dy dx, all you have to do, take dy dt divided by dx dt. Why is that all you need to do? Well, look at it, dy dt, dx dt. If you're thinking about this, dy dt divided by dx dt, well, keep change flip, right? Dy dt times dt dx. Wait, the dt's cancel. We get dy dx. So if I want dy dx for something like this, all I gotta do is find the y derivative, find the x derivative, and divide them. So dy dx for this would be 2t minus 8 over 2. Oh, I guess I could simplify that, divide it all by 2, and get t minus 4. So that would be dy dx. So dy dx is a function of time. Weird. Okay, so let's go in and look at examples. I'm glad that we see this. So I'm glad to get that pointed out to me. So if dx dt is equal to 0, that's a problem, right? We would have an undefined derivative. So that's possible. It's something that can definitely happen. But that's something just to keep an eye out for when we do these problems. All right. So find dy dx for the given curve. So this one, we have x is equal to cosine t and y is equal to negative sine t. So I'm gonna do the slow version. So dx dt is equal to negative sine t, and dy dt is equal to negative cosine t. So that means that dy dx, we just take the dy divided by the dx and get negative cosine t over negative sine t. Check yourself, what is cosine divided by sine? Oops, it easy. Cosine divided by sine is, those two go, cotangent. Nope, not x, t. So, there we go. And so for a part like A where it says t is equal to pi over 3, I can just say, oh, okay, cotangent of pi over 3. And then I can find that. So I'm gonna do a quick mini trig lesson to remind you how we get cotangent of pi over 3. If you don't need it, then skip to where you see me doing part B. So cotangent of pi over 3, we do need to know what pi over 3 is, and the way that I know this is I've got 30, 60, and 90 is kind of its own little thing, and then there's also the 45s that are kind of own little thing. So 30 and 60, it's pi over, and for me, I remember that they're kind of like flip-flopped. So this is pi over 6 and this is pi over 3. It's really convenient that that's the way that that works out. It's a helpful memory device for me. So 90 was pi over 2 because 180 was pi, and 45 is pi over 4. That's kind of the one that doesn't really fit with these two. So anyway, I see pi over 3 and I'm thinking, okay, that's a 60-degree angle. So I draw my 60-degree triangle. I know that's 1. And if this is 60, then that means this is 30. Oh, no, I don't do 1. You can. I personally, what I do is, if this is 60, this is 30, it's a 1, 2, 3 triangle. 1, 2, square root of 3. Just remember that the square root of 3 is actually smaller than 2. So small side goes with small angle, big side goes with big angle, medium goes with medium. So now if I want cotangent of pi over 3, I can do SOHCAHTOA. And remember that in SOHCAHTOA, tangent and cotangent are buddies. So cotangent is just A over O. So adjacent over opposite, so 1 over root 3 is what I would do there. And you can simplify this by doing root 3 over root 3 and get root 3 over 3, but you can go beep, and, it's going to simplify to that doing this thing, rationalizing the denominator, but you don't have to do that. So, yeah. Okay, part B. Part B says 1, 0. Oh. So now I'm not given a t value, I'm given an x comma y. And so what I need to do is I need to go x equals cosine t, y equals negative sine t. I need to find the t value that gives me 1, 0. So 1 is equal to cosine t, and 0 is equal to negative sine t. Well, what is cosine equal to 1? Cosine's equal to 1 here, right? That's at 0. So when our angle is 0. So this is going to be t is equal to 0. Oh, that's also when sine is 0. So cool. Sometimes you'll get more than one answer for these, and you've got to find the one that works for both of them. So we're finding so basically this is an extra step added in to say x is 1, y is 0. What's t? Now find dy dx when t is equal to 0. So our dy dx was cotangent t, so cotangent 0. So what I do for cotangent is I think about that, that's cosine of 0 over sine of 0, it's 1 over 0, which is equal to frowny face, or sorry, undefined, right? It's an undefined slope. We likely have a vertical slope here, or some kind of asymptotic relationship. But I know what the graph is going to look like with this. I've done these before, so it's going to be a vertical slope. I mean, I've done problems like this before. Okay. So now let's talk how to find d2y dx squared. So this one's not as straightforward. So let me give you the fancy, like, showing how this works, and then we can talk about it. So d dx y is another way to write dy dx. It's saying take the derivative with respect to x of y. If I then want to take the derivative of this, I can actually look at it like this, d dx of this. How many y's are in this? And let's look at, like, kind of how this is going to play out. We got 2 d's, so that's d squared. And there are 2 dx's. So the way that the formula actually works, the way that we take the second derivative and any successive derivative, we're going to take the derivative of dy dx. And the way that we do that is, oh yeah, right. So in our situation, I missed a step, sorry. In our situation, d dx is d dt over dx dt. That's really what's going on here. So what we wind up doing is we take the derivative of dy dx with respect to t, and then we divide it by another dx dt. All right, so if my explanation didn't work super well, that's okay. I think Stu's got a really good handle on it here. So what we're going to do, let's see, if x is cosine t, y is negative sine t, oh, same as before. So that means dy dx is equal to, we got cotangent last time. Oop, cotangent t, right? So we got dy dx as cotangent of t, just from doing this last time. If we want to find d2y dx squared, what we want to do is take the derivative of this divided by dx dt. So we take the derivative of this. So the derivative of cotangent is negative, and then what cotangent and cosecant go together, so cosecant squared t. So the derivative of that, and then divided by dx. Remember, dx dt was negative sine t. So that is negative sine t. And we could actually clean this up, couldn't we? The pluses, or the minuses turn to pluses. This is 1 over sine, so this changes to 1 over sine cubed t, or cosecant cubed t, right? Either one of those. So if I was going to take the derivative again, what we do is we keep on, so we take the derivative of what we have, divide it by dx dt. So the good thing is the way that we're doing this is going to work very similarly for polar graphing, which is, that's the next piece, and similarly for vectors. So if I wanted the third derivative of this, what I would do is I would take the derivative of that, which is going to be 3 cosecant squared t times negative cosecant t cotangent t, and then we would divide that again by dx dt and get negative sine t. So I'm not going to clean this up, but that, that's the idea. So for each derivative after dy dx, we take the derivative of our dy dx, and that goes on top, and dx dt, just another copy of dx dt goes on the bottom. And that's kind of what the square, dx squared. So in the first one, there was a dx on the bottom. In the second derivative, another dx pops on the bottom. In the third one, another dx pops on the bottom. In the fourth one, another dx. So a new dx pops out on the fourth one, and we take the derivative on the top. So for the curve given by this, find the slope and concavity at 2, 4. Okay, so here's a good rubber meets the road question. It's just got all the good details in there. Let's see how this rolls. So if x is root t, then dx dt is 1/2 t to the negative 1/2, or 1 over 2 root t. And then y looks nice and simple. Y is 1/2 t squared minus 2t. Personally, I want to distribute that 1/2. So my dy dt is t minus 1. Ooh, nice. That's great. That makes me happy. Nice and simple. So dy dx is going to be dy divided by dx, right? T minus 1 divided by 1 over that, right? So here's the thing. 2 root t 1 over something. Well, dividing by 1 over something is the same as multiplying by the regular version of it, right? So 2 root t times t minus 1. And so 2 comma 4, let's see if we can find that. So if x is 2, 2 is equal to root t then, so square both sides and you get 4 is equal to t. Okay. That's the only answer there. So that means that if 4 is supposed to be y, then 4 should be t as well. Let me just make sure that I didn't make a mistake. You know what, this is good to talk about. 1/2 t squared minus t. So this is something where I could, I actually could factor and solve this and potentially find multiple answers. So I'm gonna do that. I'm gonna subtract the 4 from both sides. 1/2 t squared minus t minus 4. I don't like that half, so I'm gonna multiply everything by 2. And 2 times 0, 2 times all that. So I'll get t squared minus 2t minus 8. So I get t minus 4 times t plus 2. And so I get t is equal to 4, or t is equal to -2. But here's the thing, -2 doesn't work in this situation. So I know -2 is not an answer that we can use. So t is 4. Okay. Oh, so I plug in 4 here. So that's 3. So 2 times 3 is 12. All right, so at the point 2 comma 4, the slope is equal to 12. So how do I find concavity? Well, then I go and take dy dx, which was 2 root t times t minus 1, and I differentiate that, and I'll divide it by dx again. So I'll take the derivative of this, and I gotta do product rule here, right? So it's gonna be 2 times 1 over 2 root t. Leave the t minus 1 alone, plus, I'll take the derivative of that and get 1, 2 root t times 1. So now we've got a big mess. Oh wait, but we're dividing it by this, so that means we're multiplying by the reciprocal, so 2 root t times, let's see, those 2's can cancel, t minus 1 over root t plus 2 root t. So that means, let's see, when we distribute this, we'll have our 2 root t times t minus 1 over root t, those cancel, plus 2 root t, 2 root t, that's 4t. So that's 2t minus 2 plus 4t is equal to 6t minus 2. It is beneficial to simplify these out. If I had to take a third derivative, it'd be much easier. So t was 4, I'll plug in 4, I'll get 24 minus 2, I'll get 22. So concavity. We don't say the concavity is 22. We would say, is it concave up, concave down, or neither? Since it's positive, we know it is concave up. Con up. All right. So we got first derivative covered, we got second derivative covered. Well, and further derivatives. The last thing, I think, yeah, okay, so we got 2 formulas to look at, and I am gonna go kind of quickly through these. They're more of a, sometimes they show up, and you just need to know them. So if you recall back, we had arc length, right? And I actually would recommend having arc length and then having parametric arc length, and then having polar arc length, and then having vector arc length. I had to remember, there's a band called Vector, and they spell it with a K, and I'm like, wait, oh no, that's the band, that's not real life. Okay. So if you remember, originally arc length was S is equal to, go from A to B, square root of 1 plus f prime of x squared dx. Parametric arc length, through a similar derivation, where is it? So, if any of you are interested, like I'm not trying to keep you from the cool math that shows where stuff comes from. I'm just trying to keep these lessons short. So it's dx dt squared plus dy dt squared. And it's dt this time, but I hope you see a similarity here. This arc length, when we're dealing in rectangular equations, is 1 squared plus f prime squared. This one is dx squared plus dy squared. So, and one we could even think about, that might just be, we could think about this as like x prime plus y prime. It's just x prime in regular rectangular equations is just 1. In parametric, x prime is dx dt. In polar, if I remember correctly, in polar it's something similar. And so I'll come back and make fun of current me in the future if I'm way off here. But if I want to find this arc length, oh, so what I was saying is I'd recommend having all of these like in the same spot so you can look at their similarities. And it helps you memorize all 4 of them if you kind of think about them in a consistent way. So I would do that with the arc length, and I would also do it with the surface area equations. Because the surface area equations, they all take arc length and add in a 2 pi and the function, and that's basically it. So I'll do one of these examples here, and then I think I'm going to try to cut the lesson there. Keeps it a little bit shorter, even though we're still at about a half an hour. Let's see. Find the arc length. So I would just go from 0 to 2. You can't see this. Okay, this problem right here. I'd go from 0 to 2. Let's see, dx dt is 1 minus 2t. And then dy dt is a little bit messier. That's going to be 3 root t. And then you can integrate that. And remember, my expectation for you is that you can plug this into the calculator. Sure, this might be something we can do by hand, but like we're just trying to get through these lessons as fast as possible so that we can get into the real exciting stuff that we do in BC. This is like covering all the backstory and stuff. And like, okay, we learned about all these different characters. Great, cool. Now let's get to the real story. So, and I'm serious. Once we hit chapter 15. 15 is where I'm going to be excited. So 30 more pages. The good thing is these are going to fly. In case you missed it, I'm already done talking about this chapter. For your homework, I would say like, maybe knock through the odds. Ooh. knock through. Yeah, the odds are, yeah. So let's say knock through the odds of them. Let me know what I can do to help. And if we need to go more in depth on any of this, absolutely we can. So hope this is helpful. Bye.